Okay, it's 11 a.m. Let's start. Good morning, good afternoon, good evening, everyone, depending on where you are in the world. We are thrilled to have you join us today for a groundbreaking webinar on safe human-robot interaction in construction, supported by the National Science Foundation. This event is a collaborative effort between the Rinker School of Construction Management at the University of Florida and the National Institute for Occupational Safety and Health, or NIOSH. As we delve into the crucial aspects of enhancing the safety of human-robot interaction in construction, we are honored to have an esteemed group of speakers and experts with us. Just the FYI, we had over 330 registration when I last checked in the morning, so I'm optimistic about a fantastic turnout. Thank you all for being here, and let's make this webinar an enriching experience for all of us. Our organizing team consists of Ph.D. student Jinyao Cheng and Zijian Zhu, alongside UF faculty members Dr. Idris, Jeelani, and me. We all worked on different aspects of this webinar to make it happen. Special recognition goes to Dr. Jim Harris, Chief of the Protective Technology Branch at the Division of Safety Research at NIOSH, whose leadership has been instrumental in making this webinar a reality. But before delving into the webinar content and discussing the timeline and some logistics, I would like to invite Dr. Robert Cox, Professor and Director of Rinker School of Construction Management at the University of Florida, to share a few words and extend a warm greetings to you all. Dr. Cox?
Yes, good morning, everyone. I'm Robert Cox, the Director of the Rinker School of Construction Management, and it's my pleasure to welcome all of you to the Safe Human Robot Interaction in Construction webinar that's made possible through an NSF grant. Special thanks go to the team for organizing this event. What a huge success when you know that you've got 320 plus registrants today. That's a huge success. We would love to do this in the future and welcome you to our campus. As many of you know, the Rinker School of Construction Management is among the nation's top construction management programs, and probably known best for being the oldest program as we near our 90th anniversary celebration. We have over 30 faculty members who are very, very active in the industry as well as in research, and we tout almost 8,000 alums from our undergraduate and graduate degrees. Our faculty members are actively involved in groundbreaking AI research and robotics and automation, and they're making significant global impacts through their scholarly activities. And we're very, very proud of all of our faculty, staff, and students as they continue to increase the Rinker legacy and the impact that they're making worldwide. So from industrial robots, transforming construction to cutting-edge aerial and ground robots, our faculty explore a spectrum of robotic technologies. We've achieved success through multiple NSF and robotics initiatives and secured multiple project funds in the Future of Work and National Robotics Initiative. We're very, very fortunate here at the University of Florida, where we have fully embraced AI, and the university's largest donation in its history supported the push for AI and the hiring of hundreds of AI faculty, specifically working within the schools, within the departments. And that also led to the development of HyperGator, the supercomputer that's globally recognized as the strongest computer in the world. So, with all that said, we welcome you to our sunny campus. I hope you have a wonderful day during this webinar. And of course, here at the University of Florida, we always sign off by saying, go Gators.
Thank you. Thank you, Dr. Cox, for your thoughtful words. I appreciate it. Now let's quickly go through the webinar timeline. As you can see, we are currently at the welcome and introduction part of the webinar. Following this, we will commence session number 1, Industry and Government Perspective, on Safe Human-Robot Interaction. This session features a keynote address by Dr. Scott Earnest from NIOSH, followed by individual presentation by Maren Roush from A3, Dr. Henning Roedel from DPR Construction, and Dr. Jacob Carr from NIOSH. We have allocated 15 minutes to each presentation, but we hope that each presentation will take around 12, 13 minutes. So it allows us for hopefully one question at the end of each presentation. But once all the presentation in this session concluded, we'll move on to the roundtable discussion, where we spend approximately 15 minutes discussing more general questions targeting all the panelists. We have already received several questions from you during the registration phase and have used them to create a preliminary list of questions. However, if you have any further questions, please feel free to send them to us through the chat, and we'll do our best to integrate them in our roundtable discussion session. After concluding the first session, we will commence our second session, focusing on academia's perspective on safe human-robot interaction. Similar to the previous session, we'll begin with a keynote presentation by Dr. Medina-Borja from NSF, followed by presentation from Dr. Becerik-Gerber from University of Southern California, Dr. Roush from the UF Industrial and System Engineering, and a final presentation by Dr. Jeelani, my colleague, and I. We hope to, similar to the previous session, we hope to entertain individual questions at the end of each presentation and then proceed to a group discussion during the roundtable discussion. Finally, we will conclude the webinar with closing remarks by Dr. Idris Jeelani. So I think this was a quick overview about how the the timeline of the presentation going to work out. And I think with that, we can move forward with our first presenter, actually. Let me... Okay, so our first session is, as we discussed, is about industry and government perspective, where we have multiple presenters from industry and government agencies to discuss the safe human-robot interaction, not only in construction, but also in construction and similar sectors that they have worked on. Our first presentation and our keynote is by Dr. Scott Earnest, who is the Associate Director for Construction Safety and Health at NIOSH. Prior to joining the Office of Construction Safety and Health in 2015, Scott was Engineering Branch Chief at NIOSH Division of Applied Research and Technology for 10 years. Scott has 70 peer-reviewed publications and technical reports. He began his career as an active-duty commissioned officer in the U.S. Army Corps of Engineers. He's a registered professional engineer and certified safety professional with master's and Ph.D. degrees in industrial and mechanical engineer. Scott, you can go ahead and start the presentation. Let me stop sharing, and you can take over from here.
Okay, thank you, Professor Gheisari. It's great to be with you, and let me share my screen. Okay. Okay, how does that look?
It looks perfect.
Okay. Good morning. I'm going to be talking with you about the NIOSH construction program, its work, and its priorities. There's a significant emphasis on the future of work at NIOSH, and part of that future involves automation and robotics. Robotics and automation is an important topic that is rapidly beginning to impact the construction industry. NIOSH is funding work in this area through 3 different groups: internal NIOSH staff that are conducting research projects, the National Construction Center, or CPWR, that we fund and work extremely closely with, as well as funding at various universities through our Office of Extramural Programs. Recently, the U.S. infrastructure bill has increased construction work going on across the country. The $1.2 trillion infrastructure bill includes spending to repair aging roads and bridges, rebuilding airports, jumpstarting transit projects, and rebuilding school buildings and hospitals. Construction is a rapidly changing industry, and safety has greatly improved from years ago. In the early 20th century, the development of elevators and cranes made high-rise buildings and skyscrapers possible, while heavy equipment and power tools decreased the workforce needed. Trade unions were formed to protect construction workers' interests, and personal protective equipment like hard hats and earmuffs came into use. This slide of construction in New York City occurred when a lot less emphasis was placed on safety than today. Construction is one of the most hazardous industries in the U.S., with 1,034 fatal occupational injuries and 74,000 non-fatal injuries in 2020. The United States in 2020 had 4,764 fatal occupational injuries and an incident rate of 3.4 per 1,000 workers. 1 in 5 worker deaths in 2020 were construction related. Construction had about 7% of all U.S. workers, but 20% of the fatalities, the largest number of fatalities for any industry. The industry includes residential and commercial building construction, but also heavy and civil construction and specialty trades like roofing, plumbing, electrical work, drywall, and painting. The mission of the NIOSH construction program is to eliminate construction fatalities, injuries, and illnesses through a focused program of research and prevention. The NIOSH strategic plan guides the work that we do under the construction program. There are 7 strategic goals that are related to the 7 health-based cross sectors under the National Occupational Research Agenda. Each one of the red goals on this slide include relevant intermediate and activity goals for the construction center. And we're focusing specifically on this for this webinar on traumatic injury. This is a chart from the National Construction Center, CPWR. It's about the Focus 4 hazards, which are the main causes of traumatic injury in the construction industry. In any given year, they represent about 60% of all the fatalities that are occurring. And they include falls, struck by incidents, caught in and between, and electrocutions. So again, this slide shows data from 2011 to 2021. And as you can see at the bottom, the orange represents the number of fatalities each year from falls. Above that, in blue, is struck by. In light blue, caught in and between, and then at the top are electrocutions. So again, there's a significant number of both falls and struck by every year. Because of this, one of the things we're doing to address it is we organize national stand-down events. And these are 2 logos that we've developed and are actually, they've been turned into stickers that construction workers wear on their hard hats, related to, on the left-hand side, the National Falls Campaign, and on the right-hand side is the struck by incidents, or the struck by incidents campaign and stand down. And so again, in May we have our falls campaign and stand down, and then in April we do a struck by stand down related to preventing struck by incidents. And many of those struck by incidents are occurring in highway work zones, either getting struck by heavy equipment or struck by vehicles that are intruding into the work zone. In the past year, we had a very well-attended webinar on falls prevention and prevention through design. And we're putting a lot of emphasis on prevention through design because to reduce hazards, it's important to focus on the top of the hierarchy, or designing out the hazards or eliminating them. This webinar, and we worked with OSHA, CPWR, Gilbane, Jacobs Engineering, had over 1,000 registrants. Prevention through design is an extremely important high-level approach to construction safety, and we're working to advance it across the construction industry. We're also working collaboratively with Arizona State University to do annual workshops on prevention through design. And because there's a very significant presence of Hispanic construction workers in the construction industry, we do Spanish language webinars as well. And that's down here in the bottom left is one we did back in the spring. Now I'm going to talk about advanced technologies. This slide comes from an ASTM conference on digital construction we were involved in. Rapid technological advances, job displacement, changes in work arrangements and aging workers, extreme weather conditions, and the pandemic have already changed the way construction work is being conducted. While it's difficult to forecast the future, we need to try to anticipate and prepare for what lies ahead. The construction side of the future will likely increase the use of advanced technologies, including drones, exoskeletons, autonomous vehicles, remotely controlled mobile equipment, 3D printing, robotics, and building information modeling. These technologies are expected to increase productivity, which is important, and quality, while reducing the cost of construction projects. In addition, the new technologies can improve the safety of workers for certain tasks, which from an NIOSH perspective is extremely important. The next several slides are related to specific applications of these technologies. Many of these approaches are being studied by NIOSH or our partners. The first is off-site construction automation, similar to modern automated manufacturing. Prefabrication is manufacturing and assembling the components off-site and transporting to the construction site. Traditionally, basic materials were transported to the construction site where all the assembly occurred. There are productivity, cost, and safety benefits to prefabrication and modular construction. Prefabrication, pre-assembly, modularization have become more viable with recent advances in information technology. These methods will grow quality, time, and labor concerns and make alternative traditional methods more attractive. 3D printing is also being used more to print complex curved layers and artistic structures for modern buildings and even housing more efficiently. And we're looking at 3D printing in the industry. Building demolition is extremely hazardous. Demolition involves dismantling, raising, and removing of any building or structure. Traditionally, heavy excavating equipment was used for demolition work. Common hazards identified in general demolition include the collapse of the building, falling from heights, or being struck by falling objects or flying debris. Automating this activity has the potential to significantly improve worker safety, and NIOSH is also studying this topic. We're also looking at automated bricklaying. Collaborative robots in masonry construction could reduce traumatic injuries and musculoskeletal disorders while reducing the need to physically lift heavy materials. A bricklayer lifting approximately 238-pound blocks a day is lifting the equivalent of 2 small SUVs every day. Similarly, overhead drilling poses MSD hazards on the body, and we've looked at that as well. Just as autonomous vehicles are coming to the streets, they're also starting to reach construction sites. Early models are already being tested and will become more common in the future. Agriculture and mining are further ahead, and the construction mining program is doing a tremendous amount of work in this area currently. Like other forms of automation, this equipment offers the potential benefits of enhanced safety, increased productivity, and higher efficiency. Motor vehicle crashes are the leading cause of work-related deaths in the U.S. Millions of workers drive or ride in a motor vehicle as part of their job, and risk cuts across all industries and occupations. From 2003 to 2014, there were about 22,000 work-related motor vehicle deaths in the U.S. In 2013, the total cost of motor vehicle crashes at work was $25 billion. Vehicles and mobile heavy equipment were a major source of fatalities in the construction industry, resulting in 7,681 deaths between 1992 and 2010, and about 404 deaths each year. From 2008 to 2010, vehicles were the source of more than half the fatalities at road construction sites, vehicle intrusions, and accidents within the work zone. Finally, I wanted to mention drones and exoskeletons. Drones are the most widely used emerging construction technology. They can conduct site surveys more quickly and accurately than a crew on the ground and are cheaper than aerial imaging. Their high-resolution cameras can collect data and create interactive maps. Another benefit of using drones is safely inspecting hard-to-reach places, such as on bridges or tall buildings, to reduce fall hazards. Again, the number one cause of construction worker fatalities. Drones can also monitor progress on job sites. And then exoskeletons. Initially developed for the military and for medical use, they're now beginning to appear on construction sites. Helping to protect workers from MSDs and hand-arm vibration, these devices can augment humans and can increase productivity. Lower back pain is affecting nearly 40 million workers, and it's a common issue in construction. Exoskeletons are being used in manufacturing and tested on construction sites to drive the development of uptake of exoskeletons across the industry. We have several ongoing research projects and we've done numerous science blogs on the use of exoskeletons in construction. Some trades are most likely to be impacted by greater use of automation and robotics. These include brick and stone masons, cement and concrete finishers, carpenters, drywall, and cement masons. Each of these trades are labor intensive with significant exposures to falls, struck by hazards, electrocutions, and musculoskeletal disorders. Robots are particularly beneficial in sectors with challenging labor conditions and a need for greater productivity. The higher number of work-related injuries and illness in construction is an important factor. Robots can handle heavy loads, perform dangerous or dirty work at inaccessible locations, and in locations requiring awkward postures. Some of the advantages of greater robot use are on the right, such as work quality, productivity, the cost of labor, lack of adequately skilled labor that's available, or disadvantages on the left, mobility, cost and complexity, the fear of change, lack of guidance or comprehensive guidance, and liability concerns. So that concludes my presentation, and I'll go ahead and hand things back to Professor Gheisari. Thank you very much.
Thank you, Scott, for the great presentation. I really appreciate it. So I can take the, let me switch back to my presentation. To share the screen. So that way we can, others know where we are in our presentation. So just, there was a question asked, like, and it was not necessarily about the NIOSH, but like it was much more about how is NIOSH or similar industries, some government agencies positioning themselves to address the rapid presence of various types of robotic in the construction. Like we could see different type of robot, from ground and legged robots all the way to aerial or humanoid robot. And you also mentioned, like, right now we see also autonomous vehicles, not only on the highways and streets, but also they're going to show up on the construction job site. How can we ensure their safe integration? What, like, how NIOSH position itself to address these rapid changes?
Yeah, that's a good question. I mean, we're putting a lot of emphasis on it. We set up a Center for Occupational Robotics Research several years ago, and I know later in this session, Jacob Carr is going to be providing a fair amount of detail about what that center is all about and the work that's going on. But we're putting a significant amount of research and research dollars into this particular topic, both internally with internal researchers through CPWR, who we fund as a National Construction Center. And also we're funding various universities to conduct workforce in this area. So we view it as extremely important, and it's, quite frankly, it's the future of work.
Thank you so much. Like, do you see any collaborative effort that you might have in future with other funding agencies or other groups? I knew like NIOSH at one point had some collaborative funding opportunities with NSF, like the funding was coming through the NSF. Is there, do you see, or do you foresee that we will have such opportunities in the future again?
I would say definitely. I mean, we view working with partners as extremely important, and one of the ways we do that is to make funding available, to collaborate with our partners to advance occupational safety and health, not only across construction, but across all industries.
Thank you, Scott. I appreciate it. So we'll get back to you again as a part of the roundtable discussion. Thank you.
Thank you.
So I think we are right on time. We are in good shape, actually. So now we can move forward to our next presentation by Maren Roush. Maren is the Manager of Standards Development at A3, the Association for Advancing Automation. A3 is the North America's largest automation trade association, representing more than 1,200 organizations involved in robotics, artificial intelligence, machine vision and imaging, motion control and motors, and related automation technologies. At A3, she worked with experts from around the world on ANSI and ISO committees to develop US and international standards related to the industrial robot safety. Maren, let me unshare my screen, and then you can take over and continue.
Okay. Can you hear me okay?
Yeah.
Okay. Yeah, so thank you for the introduction. Let me just figure out how to advance my slides. There we go. Yeah, so I've been with A3 for about 2 years now. And my previous experience was with NSF, which is not the National Science Foundation in, as we think of it, but the National Sanitation Foundation, or yes, they got rid of their national in the name and just went by their call letters. And so I'd spent 26 years there developing standards related to public health. And my experience was really with drinking water filtration and biosafety cabinets. So I'm somewhat new to the robotics industry, but thankfully I do work with experts from around the world to help develop standards. And, you know, I'm kind of just picking their brains. So hopefully if you have any questions at the end of the presentation, I can answer them, but if not, I certainly know who to get in touch with. Let's see. So this is I don't know if that's Mr. Bean or just a guy that looks like him, but when we at A3 speak about standards, we are talking about voluntary industry consensus standards. And I will unpack that definition in just a minute, but the important thing about standards is that they enable things to work smoothly and consistently around the world. And here are a couple of examples. A world without standards, if you've ever traveled internationally and you want to plug in your electronic gadgets in your hotel room or in the meeting space, you might need an adapter to use your existing plugs in that country. And the reason for this is that different regions around the world had begun to create their electrical infrastructure prior to international standardization in that area. And in a world with standards, you might be able to turn on your phone and look for Wi-Fi. Well, there are international standards for Wi-Fi. And so that means that no matter where you are in the world, you can generally turn on your phone or your computer, search for Wi-Fi. And if there is a network available and you have the passcode, if it requires one, you can log in. And that is a benefit of standardization. And USBs are another example of that. So a standard is a voluntary means to achieve a desired outcome. And this is a lot of words, and I know it gets a little bit dry, but it really is critical to safety and ensuring that everybody is playing on a level playing field. In the US, we are governed by a national accreditation board or body, and that would be ANSI, the American National Standards Institute, that will oversee American national standards. And internationally, we're overseen by ISO, which is the International Organization for Standardization. And standards provide both normative guidance, and normative is required according to the standard. And informative is, well, you should do this, but you could still conform to the standard without complying with this particular piece of it. We have committee volunteers that spend their time and energy and many, many hours reviewing documents and scrutinizing individual words that help us write standards. And we also have to get representation on the various committees from the different stakeholder groups. So in terms of robotics, we would have robot manufacturers present in the room, but we would also have integrators and researchers, government bodies, and users of robots, because all of those people bring different viewpoints to the table and may have different concerns about what is ultimately in the standard. So this is a little bit covering the same information that I just went over. We do work towards consensus. It is not always unanimous, and it is kind of humorous to sit in meetings of our committees that write the standards, because they get heated. It seems like a very dry activity, but people do understand the monumental results of the work that they're doing in terms of what manufacturers have to conform to, what their design features are, what they're allowed to market eventually in their sales. And then, obviously people want to be safe. So you may have somebody pushing for something that's faster to get more work done, but when you have individuals in the room that care about safety, particularly human safety, they speak just as passionately about, well, fast is great, you get the work done, but we need people to ultimately be safe using this technology. So those are the different viewpoints that go into writing a standard. And this is, when we use the word standard, it's not the same as an OSHA standard, which is a government regulation. Both ANSI and ISO standards are considered voluntary, not regulated. However, if those standards are describing the current state-of-the-art best practices, and a manufacturer or integrator is not using the standard or not following its best practices, then if an accident were to happen, they would have a very difficult time justifying that they were doing what they believe to be right. So we don't normally need a lot of strong arming to get the good companies to agree to conform. They're with us every way of the process, helping to write the standards and then ensuring that they're followed. There is a public review period of standards prior to them being published. And in order to stay abreast of what standards are coming down the pike, you may want to subscribe to ANSI's Standard Action. And that is a weekly newsletter that comes out electronically. And it discusses all of the standards that are under development in which technology areas and how you can participate in that process. So we have a couple of standards at A3 that have been developed as part of the ANSI process. And these are for industrial robots. And industrial is not exactly the same as construction, but it's obviously there's a lot of overlap, and the same robots can be used in different applications, whether it's industrial or construction related. So that's just my disclaimer, is that the specific scope of the A3 standards is industrial robots. There are additional concerns that would come into play in construction facilities and situations. So I apologize for all of the, these slides are a little bit dry, but this is my work, so I'll try to keep it interesting. There is a standard, ANSI R1506, and that's what we call it. That is a direct US adoption of an ISO standard, 10218, and that discusses what requirements are in place for industrial robots and robot systems. And as a result of the adoption of that standard, there are the following technical reports that were written by A3 that discuss various associated topics, such as how to perform a risk assessment. And that document in particular is used in many areas outside of robotics. It's just a good format for doing a risk assessment and what steps to take and how to document it. So that is a pretty popular technical report that came out of this work. And then there's user responsibilities and test methods. But these are all developed by A3. And I should note that A3 used to be called RIA. It was rebranded a couple of years ago. So if you were searching for these standards online, you may want to put in RIA instead of A3. But the call numbers are still the same. And R1506 does focus on safety for industrial robots. And these are considered fixed in place manipulators, robots with manipulators or arms. And there are two parts to the standard. Part 1 lists the requirements for the manufacturer of the robot. And then part 2 addresses the integration of the robot into a robot system. And what's interesting is that as time progressed, so R1506, I think, was developed in the early to mid 1990s. I could be wrong there. But technology is advancing faster than standards can be written, and even faster than code can be written into regulations. So it became quickly apparent that although R1506 didn't exclude mobile robots, it didn't particularly do a good job of addressing them. And so with that in mind, our committees worked together to develop R1508, and those are safety requirements for industrial mobile robots. And then R1508 Part 2, again, is for the integration of mobile robots into their systems. R1508, I think, was published just a couple of years ago, and then actually in November, Part 2 came out. So it's a brand new document, just hot off the presses. And our committees went into a lot of discussion with respect to what would be included under the scope of the standard and what would be excluded. So there are already standards that address fork trucks. Those were excluded from R1508. And same with vehicles with the capacity to transport one or more riders. However, included in the R1508 scope are there's going to be no uncontrolled public interaction of individuals with the robots. They could be used in a facility that has visitors touring it, but those visitors to the plant would be controlled by their guide, their tour guide. So there could be some untrained public people going through a plant, and the standard would still apply to the robots used there, but those instances would be controlled by tour guides, like I said. The standard doesn't say whether it addresses robots that are used outdoors versus indoors. They could be used for either. And it is also silent on the topic of wheels versus tracks and versus legs. So just getting into the nitty-gritty of robots for individuals that may have used some but not others, or just want to have a quick breakdown. I should pay attention to the time. There are the following basic components: the manipulator itself and control system, power sources, sensors, teach pendant, and then the end effector and associated equipment. And I'll go into those in more detail on the next slides. So the manipulator does not include the end effector, and there are manipulator hazards that exist, and those include being struck by it or being crushed, pinch points, laceration by sharp edges. And so when doing a risk assessment of a robot installed in a particular situation, you have to consider whether somebody could be struck by the manipulator or also crushed between it and any safeguarding that might be present. So it's also looking at what's in place once it's fully integrated into its end location. And then the box shows up there. The controls include power for the manipulator and for the teach pendant, components within the control box, and then any computers or microprocessors. Now, the controller does not necessarily include controlling the end effector, and so that must be considered in addition to the robot controller when looking at the risks associated with the robot. These are just a list of sensors that you might see. Put that up for a second. That's not an exhaustive list either. And then the teach pendant that is used while in manual mode. And then finally, the end effector. They can include functions that, such as vacuum, gripping, welding, drilling, cutting, trimming, lasers, and vision systems. So each one of these different bullet points under the various functions for end effectors present a unique set of potential hazards that people working with the robot could be exposed to. So I think I talked earlier about how R1506 was developed a decade or 2 decades ago, and it really had to do with industrial robots that are used in, say, manufacturing of automobiles or in these vast industrial facilities. But as time has moved on, the industry has developed more collaborative robots that can be used hand in hand with workers and still be safe. And that is, I'll move into that in just a second. I'm also keeping an eye on the time, which I know I'm quickly running out of. So practical steps for keeping safe with robots, you can read that. And then looking at collaborative robots, which are also addressed by R1506 and R1508, as they've been revised at least every 5 years, we are required to take a look at the standards and update them to address advancements in technology. So with collaborative robots, there are new concepts, newer to the standards, such as the safety-rated monitored stop, hand guiding, speed and separation monitoring, and power and force limiting. And so if you're looking at a robot and are trying to figure out whether it is one that's designed to be used in a collaborative application, these are some examples of ones that are, and typically they'll have the rounded edges, softer surfaces, smoother surfaces, and usually with smaller payloads as well. And then I would be remiss to not mention that there is an alliance, an official alliance between OSHA and NIOSH and A3. And we're working together to promote education across our different organizations and to employers of workers, and talking about the best practices in industrial robot safety. So I think I made it with 1 minute to spare. Thank you.
Thank you, Maren. Thank you so much for your presentation. Let me switch to my presentation now and share my screen. Thank you for your great presentation. Like I sat on one of those standards development. It was for drones and how we can use them for inspection on the sites. And oh my God, the amount of effort that goes into just putting together that, like it took over a year, and then for public feedback, and then it turned into a standard. But I understand that development of standards, especially for human-robot interaction, is a time-consuming process that requires extensive feedback, input from various entities for preparation, final approval, and implementation. But how the whole standard development agencies and entities are effectively navigating the rapid integration and changes occurring in automation and robotics, how they can go hand in hand with that?
Yes, it's really, we are very thankful for the various committee members that sit on the standards development committees. So they will come to a standards development organization like A3, but also there are ones like UL, ASTM writes test methods. There's a whole number of standards development organizations that each focus on a particular technology area. And where there is an interest, then we can make it happen. For A3, our standards development is funded by, for A3 staff members who serve as administrative staff, it's funded by the trade organization itself. That is for, all of A3, more than just robots. It's also vision standards and imaging and AI and all of this. But a portion of the revenue that comes in from the trade organization is allocated to standards development, because that's something that our board of directors has considered a very important activity for keeping people safe and therefore promoting the whole industry. If people are dying, then robots aren't going to sell as well. So it's in our best interest to keep things safe and keep communication and discourse going across the different people who are involved in the industry. I do know from my previous work experience with NSF International, sometimes manufacturers would fund the development of standard because it might be that they were using bits and pieces of different test methods to demonstrate that their product was safe, but they wanted to get a third-party certification saying, hey, we're certified, we've been tested by somebody other than our in-house engineers, and it's been proven that our product is safe and is manufactured consistently over time. And in that case, they could pay for all of these people's time to get together and write a standard, and then with the assumption that they would also pay to have their equipment tested and certified. And so you could then look online. UL has a great database for looking at products that have been tested. You're probably familiar with their electrical safety, but if you buy a lamp from Target and you're curious if it's UL listed, you can go right online and see, okay, it was tested to the standard and it passed. So yes, where there's an interest, we can make it happen. And it just takes thousands and thousands of hours of people's time.
Thank you. Thank you so much for your great presentation. I appreciate it.
Thank you.
So let's move forward to our next presenter, Dr. Henning Roedel. He's the robotic lead at DPR Construction and Everforward International General Construction Contractor, specializing in technically complex and sustainable projects. He served as an expert in robotics for DPR, helping to source, pilot, and craft the implementation strategy of these new technologies across the company. He received his doctorate degree from Stanford University, where he invented a new type of concrete for construction on the moon and Mars. Hopefully, you will have a few slides on how we can colonize the moon and Mars on your presentation. It's all yours, Henning.
Thank you. Thank you. Unfortunately, I skipped those slides. There's different safety considerations in space, but let me share my screen and present to the workshop here some of the work that we're doing in applying robotics on job sites. So a little bit about DPR Construction, who we are. We're the 6th largest general contracting company in the United States. And we're also a self-performing general contractor. So about half of our staff are people who are working on job sites and putting work in place. And so my colleagues are directly impacted by my work, and it also helps inform some of the decisions we make as to what systems we're applying. So I'll start with the robotics mission and a little brief history. I proposed we start the robotics group in late 2020 and was approved to do so in January of 21. This was the mission statement. We enable construction to happen anywhere by anybody. And of course, anywhere includes my passions, which are in outer space. I have to caveat that that is not necessarily shared entirely by my employer, and that's okay. And then by anybody, which is where we're trying to use and adopt technologies that level the playing field, especially out in the job sites. When we focus on robotic tools, we're trying to address several challenges, and I think of them as safety, productivity, and data. Those are some of the solutions that these robotic tools provide for us, and they're big sore points for the industry. And obviously, I like to say we place robots in harm's way, and you'll see that in some of the examples that we've tested out. But we're also hopefully creating jobs for a new workforce. The industry is suffering from a massive labor shortage. The millennial and Gen Z generations are just not coming to the trades. And so ideally, we can extend the careers of our current workforce by giving them opportunities to connect to job sites remotely through robotic tools, but also attract new talent to our industry, whether they're developing solutions or they're operating these machines. We're really excited about the potential here. And then finally, the data collection analysis. Each of these tools now is smart, that knows what it's done, and that data can be aggregated into heuristics for our industry, and really knowing what we're actually putting in place, how we're putting it in place. And that's just a boon for our industry that's relied typically on hearsay and assumptions written down by people. I'll start, I'm going to list out just quite a few examples of systems we've put in place. Dusty here is what kicked it off for us. It is a field printer robot. It localizes itself with a total station, robotic total station that's off-site or off camera here. And it's basically putting blueprints on the ground, right? It's a printer on wheels. And with field robotics in general in construction, mobility is a key facet. And I always like to say construction is very much like manufacturing, but there's a key difference, right? In manufacturing, the work comes to you, and in construction, we move to the work, right? So with Dusty, this is the first robot for us to scale. In terms of some of the safety aspects that we highlight here, we're reducing exposure to chalk, which has silica components, which is very hazardous. Also reduced kneeling and bending exposure, reduced stress as well for the workers from context switching. So typically the people who are performing layout on our job sites are some of our most senior trusted people, and their skill sets are wide and varied. And so now they can continue to focus on handling exceptions on the job site, and we can hand over the activity to perhaps a little, a less experienced individual who knows how to operate the machine well. You can see some of the statistics, and I'll point out that we've, in my 2 years of running robots here on job sites, I'm aware of 2 near misses. And so this is one of them. The current Dusty platform does not have edge detection sensors like a Roomba might. And so we did have an occasion where the robot fell into a concrete opening. It was on the first floor. The robot was scuffed up, but continued to operate the rest of the day. Of course, that could have been a near miss if it had been near the, a higher floor of the building, or was a larger fall. The next technology is Vita Inclinata. It is a device that goes between the crane hoist and the load. And its intended task is to reduce the use of taglines. The machine is a spreader bar with ducted electric fans. The fans are used to rotate loads remotely with a remote control. You can see here in this pic, this was our first pilot of the technology that was happening this May of 2023. And here we're disassembling the tower crane on the job site in a very narrow, busy and compact hospital campus. And so we were able to drop that in safely, rotate the load mid-pick. The traditional technique, which would be to carry a tagline, a roll of rope over the roof, bring it over to the edge, drop it down to the edge, and then have someone on the ground carry it and then try and swing this load, all while the wind is blowing and the air is, and the load potentially could start rotating. So this increases safety quite dramatically. We've also, on this pilot, the main use case was actually for installing glass panels, but we tested a lot of various sort of loads to make sure the system was responsive and safe. But with the glass panels, we saw a productivity increase of 100%. So basically from a 40-minute cycle time to a 20-minute cycle time on average, with no safety incidents, I should say, and tremendous savings. You'll see the benefits here. We've also used the Hilti J-Bot, which is an overhead drilling robot. On our latest pilot again this year, in the spring of this year, we had the robot actually drill 33,000 holes with 0 related incidents or injuries, and a productivity gain of about, I think on average, we're estimating about 6 to 7x improvement. We had some days where we had 10x improvement. We had some days where the machine broke down and it didn't work quite as well. But that's okay, because in experimentation, this is what we're doing and what we're learning. And we're very happy with this. It also reduces exposure to the drilled concrete, and we can use it also concurrently with other machines on site for putting work in place, like Dusty. This next one is Field AI, which is more of a software company for robotics, but they have some of the best autonomy software and algorithms that we've come across. So you can see in the video that the robot here it's a 4-legged spot dog from Boston Dynamics, and it's walking around our Newport Beach office, exploring and mapping the space. And we're now using it on a job site here in this bottom right-hand corner image. And it is going through and taking photographs, which is a very dull task. We have about 1,700 photographs to take per floor, and it's a 5-story project. And so here we have a lot of ideas about how we can apply this technology. The company behind it has demonstrated multi-robot control. So in addition to quadrupeds, flying robots, wheeled robots, and so potentially running all those tasks concurrently and sharing data amongst the machines to improve their mission planning. So very excited, and we're just in the early stages of piloting. The dog is walking as I speak right now in Santa Clara. And then we have Raise Robotics. This is a robot for highly dangerous edge of slab work. Currently, it's able to install window brackets or brackets for curtain walls into concrete cast structures. We've had an early deployment with them when they were doing their initial field testing. I'm proud of that, a little feather in our cap. And we have a pilot scheduled for Q1 of next year to test that. We're also working with them to develop concrete doweling tasks. And that's when 2 slabs, an existing slab and a new yet to be poured slab will be cast right up next to it. And we need to drill and install rebar dowels to connect the 2 slabs structurally. And so this robot could potentially do that for us. And that's a massive task in our industry. It has applications beyond just building construction. This happens quite often in highway construction as well. This is the robot also had the second near miss that I'm aware of, where during the field testing, they dropped one of the bolts over the edge of the building, right? And that was a several-story fall. That led to them developing a catching net for one of the arms. So the arms can actually perform tool changes on the chassis for various different tasks. Canvas for drywall finishing. I know I'm out of time, so I'm going to skip ahead. This machine reduces exposure to silica, reduces repetitive stress injuries, and supports our notion of robots in harm's way. And then finally, exoskeletons. This is actually something we've tested extensively. We've done unpowered exoskeletons, and we've found that they actually don't work in our environment. That our craft colleagues prefer not to have them, because when they are working in overhead tight spaces, the suits typically catch on the equipment that's already up there or is already installed. They're not designed to carry their tool belts, and something as simple as that actually has a profound impact on our craft. They live and work by their tool belts, and if they can't comfortably put them on, then the suits will go. So in terms of lessons learned over our piloting history, pretty much we've found safety improvements in almost every single robotic system that we've tested. Currently, I would say the likelihood of a safety incident is low, and that's due to the fact that there aren't a lot of systems in place, right? So we don't have a lot of robot hours and robot-human interaction hours, but as time goes on, I think that will go higher. We'll start to get some likelihoods and some incidents occurring. Production typically gets you to scale. Safety and quality will get you onto a job site, but production will get you to scaling across job sites. And that the adoption of this technology takes a little bit longer because the tech de-risk is just that much more complex. And finally, do expect business models to change as the products themselves mature. So typically we found the startups and the companies developing these systems will be hands-on, and then as they get more comfortable with the system, they'll hand the controllers over to our staff.
Thank you so much, Henning, for a great presentation. Let me switch to my slides, and then I can have one question for you. Let me share my screen. Carefully created this VR here so everybody knows where we are in the presentation. So thank you so much for the great presentation. Like again, on the last slide, actually you mentioned that we don't have that many robots right now on the job site, and maybe that's one of the reasons that the safety incidents might be like very low. But like I have a more general question that the construction has historically lagged behind other industries in terms of technology integration. But we are witnessing that increasing number of construction companies embracing like these new type of robots on the job site, especially because the like 4 legs robot now are way easier to be implemented on the site. But do you believe this signals a fundamental shift in the industry's mindset, or it's just one of the questions put it as a temporary buzz with no substantial impact on the actual construction work? What's your thoughts on that?
That's a big question. So in my mind, it's almost too early to tell. So similar to the fact that we haven't had as many safety incidents, it's hard for us to say with real data to say that, you know, we're in some sort of revolution, right? We just don't have enough robots scaled in practice. Now we are seeing disruption to our business practices, and we're we're actively pursuing that rather than shying away from it due to some of the productivity gains, right? So we see the value of these machines, and we are, like I said, the labor shortage in our industry is real, it's painful, and that's enabling the use of these robots. Whereas maybe in past attempts where labor markets were a little bit stronger, the thought of replacing jobs with automation may have been cast aside. But at this point, I think our backlogs are so strong, we can't build fast enough with the current workforce that we have, and we need to improve our production rates.
Perfect. Thank you. Thank you so much, Henning. I'll get back to you again in the roundtable discussion. So let's go to our last presenter in the industry and government perspective. Actually, we start with NIOSH. Now we're going to wrap up again with NIOSH. We have Dr. Jacob Carr, who is the Deputy Branch Chief for the Health Hazard Prevention Branch within the Pittsburgh Mining Research Division of NIOSH. He also serves as the coordinator for NIOSH Center for Occupational Robotics Research. Jacob earned his bachelor's and master's degrees in mining education from the University of Nevada, Reno, and his Ph.D. in energy and mineral engineering from Penn State. Jacob, it's all yours. I can end my presentation and you can take over.
Excellent. Thank you, Dr. Gheisari. All right. So, as we mentioned, we're coming back to the NIOSH perspective on things. So Dr. Earnest at the beginning talked a little bit about the construction safety program and a higher level overview. I'll dive more into some of the details on what we do specifically related to robotics, not just in construction, but in some other sectors as well. So our work in the robotics area is coordinated through the Center for Occupational Robotics Research. This is a virtual center that we established about 6 years ago in 2017. We don't have a brick and mortar location for this center, and we don't have dedicated staff. It's really a virtual center that coordinates research across all of the NIOSH locations across the country that you can see on the map there. And we incorporate, expertise from throughout all of the divisions of NIOSH, from engineering to human factors, and a wide range of other backgrounds. And this is encompassed within our future of work initiative, because we really see that this is part of the new nature of work moving forward. The mission of the center is to provide scientific leadership to guide the development and use of occupational robots that enhance worker safety, health, and well-being. And to speak a little to the scope of what we do have research that touches on traditional industrial robots, things like robotic arms that you would see on a manufacturing floor. However, that really is not the primary focus. The primary focus for us is on these emerging technologies, such as collaborative robots, coexisting and mobile robots, wearable robots, and by that we mean exoskeletons, remotely controlled and autonomous vehicles and drones, and then more and more robots that utilize AI to enhance their capabilities, but potentially introducing new safety considerations with those new capabilities and with the incorporation of those strategies. So, like I said, the focus for us is not necessarily on traditional robots, and really the reason for that is that it is a well-established field. There have been robotic arms in factories for over 40 years, and there is a very well-established good safety record for those. It is somewhat difficult to find surveillance data for robotics-related injuries. The surveillance tools that we have really just don't fully capture those robotic-related injuries and fatalities. But the data on the screen here is from an analysis that we published earlier this year, looking at data from the Census of Fatal Occupational Injuries from the Bureau of Labor Statistics. And from 1992 to 2017, we were able to identify 41 fatalities, which is, tragic, of course, but the scale, of these fatalities compared to other sources of injury and fatality in the workplace is relatively small. We did note that most of these involved stationary robots. Most of them, 78%, occurred in the manufacturing industry. Most, 78% again, involved a robot striking a worker, and then a slightly smaller percentage, 59%, occurred during maintenance of the robot. And this is really just a reflection of where the robots are right now and what they're being used for right now. The introduction into other sectors, other work environments, as that advances, we may see more injuries occurring in those new settings. And speaking to those new settings, we do see that emerging technologies really, are expanding where robotics is being used. We see drones and autonomous vehicles being used in open spaces, in public spaces, collaborative robots, as was mentioned, exoskeletons. The world really is changing with what sorts of technologies are available and the sorts of challenges that are presented by those. One construction-related case study that we can look to, and again, this speaks to the challenge in surveillance data, that it's tough to find specific surveillance data for robotics, but NIOSH does fund, through partnership with state organizations, through the Fatality Assessment and Control Evaluation Program, or FACE program, investigations into incidents. And this is one involving a demolition robot where a worker was pinned between a demolition robot and the walls of the area where it was working. So using case studies like this, we can identify scenarios or occupations and work environments where some further research or further attention may be needed. All right, so with the time I have, I'm just going to go through a few examples of research that we do within NIOSH, and I've tried to pick a few that are relevant to construction. And these are across a wide range, from basic and etiologic research, where we're trying to understand really how and why injuries happen, intervention research, meaning that we want to identify opportunities to better protect workers with robots as an intervention, but also looking to whether interventions are needed to protect workers from the new hazards introduced by robots in the workplace. Research translation, and taking it from a demonstration in the lab or on the shelf and getting it to the actual point where it can be utilized by employers to keep their workers safe. And then surveillance, again, is a big challenge in robotics. So trying to come up with better ways to improve our ability to keep track of those injuries that are occurring. All right, so getting into a few examples, as Scott mentioned earlier, work at height and falls from height is the leading cause of fatalities in construction. And we know that drones, are more and more being introduced into the workplaces. They have a lot of different applications. One concern that we've investigated is the potential for drones being used in the workplaces to cause distraction. a loss of attention or a loss of balance on the part of workers as they're standing in the workplace, seeing these things fly around, can it cause them to lose their attention or lose their footing, and potentially introduce new hazards? So we've done research in virtual reality environments on that. Another project that is ongoing, coming into its third year, I believe, on the identification of hazards and risk factors for demolition robots. Again, this is trying to understand how and why accidents occur with these sorts of technologies in the workplace. A new project that we've just started this year is on smart masonry robots for struck by hazard prevention. This is getting to that collaborative robot concept where you have workers and robots working not only in the same space, but on the same task in a collaborative manner, where contact between robots or contact, with the same piece of material can occur not only, inadvertently, but by design in the task. So this project is really trying to understand how can we, use technology to better protect workers with novel technologies like this. And then the last example I'll bring up is a study on the investigation of safety and trust when working alongside autonomous mobile robots. So this really applies maybe more to the warehouse sector than to construction. But the whole idea here is if you have workers and robots moving around in the same environment, how does that affect the behavior of the workers, the perceptions of the workers, and the trust that they're able to place into these robots, and the trust that they have that they'll be safe as these different sorts of interactions occur, and the robots and the humans move around each other. I'll also just mention briefly that we do fund extensive research extramurally. So the examples I've given so far have all been intramural research that we've conducted in-house at NIOSH. But we also have a large contracts and grants program to fund work on drones, on exoskeletons, on autonomous equipment, on a really wide range of different topics. And then finally, I'll just mention some of the partnerships that we have. These really are critical to our success. This is how we make sure that the work that we're doing is relevant to the industries and relevant to protecting the health and safety of workers. This is how we are able to get into work sites to conduct studies, and this is really critical to our success. So I'll just highlight a couple that are relevant. One is with the National Science Foundation, and we have funded projects through the NSF's National Robotics Initiative, which is now sunsetted. But two that are ongoing right now are work on wearable robots for lower limb protection, and then also robotics for protecting workers in nursing. The other partnership that I wanted to highlight, and Maren mentioned this earlier, is the alliance between NIOSH, OSHA, and A3. This has been going on since 2017, and it's been really a fantastic way to coordinate activities across those groups, as well as to put out some good educational materials and things like that. And then also through that, as well as through other interactions, these are just some of the standards that NIOSH workers are involved in. So the 1506 and 1508 standards through ANSI and A3, as well as others related to exoskeletons, drones, and autonomous vehicles. With that, I would encourage everyone, if you are looking for more information on what NIOSH does on robotics, to visit our webpage, which is that URL at the top, which is a little ungainly, but if you search for NIOSH Robotics, that's probably the best way to get there. And what I would say is when you go to that page, if you go down to the bottom, there are some useful links on more detail about our research, both the intramural projects and the contracts and grants, some more information on those partnerships and other partnerships that we're engaged in, and then a library of different publications that we've got on the research. And with that, I'll take any questions.
Thank you, Jacob. Thank you, Dr. Carr. It was a great, informative presentation. Let me share my screen to... Thank you. Thank you for the presentation. Like I had a question. Actually, you covered it a bit, but you about like the whole like how can government agencies like NIOSH individually or in collaboration with other organizations like NSF, DOT, support research on safe human-robot interaction. Like I know some of them, like the NRI one, already sunset down. Is there any current or future plans for supporting such efforts?
Sure. So NIOSH does directly fund contracts and grants, and there are different mechanisms that are in place for doing that. You know, it is a bit disappointing from our perspective with the NRI program sunsetting, because that was really a very well suited avenue for us to collaborate with. But you know, that's something that we're still looking for other means that we can go about to do something similar to that. I don't know that we've quite found it yet, but you know, there are direct funding opportunities, as I said.
Yeah, I think we have Dr. Medina-Borja from NSF who will be presenting in our next session, and I will ask the same question from her, that how NSF is trying to collaborate with NIOSH or other similar organization to support the research. Perfect. Thank you so much, Jacob. Now I think we can start the roundtable discussion. I think I can unshare my screen so we can have all the panelists on session one. I think we are not in terrible shape. Let me get out of my presentation mode. Yeah, thank you all. Thank you, Dr. Earnest, Maren, Roush, Dr. Roedel, and Jacob, Dr. Carr, for doing amazing presentation. Now, like I wanna, as I told you, we received a bunch of questions while during the registration phase, and we put together, like I have 2-3 questions. I want to put it on the floor and see and like you, each one of you, like you can jump in and respond to the question. I had a pretty long version, but I really like the question. I want to ask it from everyone. How can we create global standards for construction automation and robotics to address safety concerns? Currently, many solutions exist at isolated case studies without practical application in mainstream scenarios. While the importance of smart and safe worksite planning for robotic environments is acknowledged, efforts to integrate intelligent technology for prevention through design and planning are limited and dispersed globally. How can the safety community, in addition to the other government agencies, establish an international task force to develop comprehensive global standards, ensuring a more cohesive and effective approach to safety in construction automation and robotics? Actually, this is a short version of the long version question. So any thoughts?
I'll speak up, but again, as I mentioned earlier, I'm not an expert in the construction field. At the international level, there are various technical groups that work on areas of technology. So when we are developing international standards under, it's called ISO TC Technical Committee 299, that deals with robots in industrial applications. So what I think I would do, not knowing about the construction industry as well as I do about my current scope, is I would look through the ISO lists of TC, their technical committees, and see if there are any that are tangential to robots in construction. So it may be that there's already a construction group working on standards, but they haven't considered delving into robotics in specifically. And in that case, if that was something that they wanted to work on, they could partner with the ISO TC 299, which already has these robotic standards, and help adopt them into a new field. So at the international level, I would recommend working with ISO. And I could volunteer to do a search of their various technical committees and see if there are any out there existing that could be repurposed for that use. Otherwise, it's working with the your national standards body, which would be ANSI in the US, and kind of lobbying the importance of developing standards in this area and seeing if they could recommend a standards development organization and or other partners to go into that effort together and start gathering the great minds around the world to work on that project.
A quick follow-up on that, like how ANSI and ISO work together?
Yes, ANSI is it's the American national body for standards development. So they are the one that accredit any American national standards. So there's probably, I don't exactly know, maybe 80, 100 different organizations that are accredited through ANSI to develop standards. So they make sure that we're being impartial, that we're representing all the various stakeholder groups, that we're following a certain set of procedures so that if there's complaints, they're addressed in an appropriate manner, that we're documenting standards development every step of the way. So they provide this overarching structure for standards development organizations to work under. And then they have counterparts all around the world. So in Germany, it's DIN, D-I-N, and then there's the Swedish Institute of Standardization, and Japanese and Chinese. So every country that is involved in the international standards work will have their own country-based one. And so what is preferred is to take standards that are developed at the international level and then adopt them as national standards, because we've already taken into account all the different legislation that exists worldwide. So like for robotics in the US, if you're using an ISO standard, there's already been this assessment comparing it to the machinery directive in Europe. So we're pulling this ISO document over into the US. If our US manufacturers want to sell in Europe and they're complying to either the American or the ISO standard, they know that they'll also conform to European regulations, sorry. So ANSI kind of reports up to ISO, and then also they take ISO level information and disseminate it down the chain of command as well.
Thank you. Thank you.
If I could just briefly weigh in on this, when it comes to construction safety standards, there's an ANSI A10 committee that we're heavily involved in, and there's, I don't know, 50, 60, 70 different standards on all sorts of different aspects of construction safety and health that we participate in on a regular basis. And that's again a voluntary consensus standard body. However, we also work extremely closely with our sister agency OSHA that puts out legally required standards for the construction industry. And so we interact with them on construction topics, on pretty much a weekly basis. And we collaborate and work extremely closely with them on construction safety and health, as well as on robotic issues. I don't know if Jacob is able to speak to that or not, but I know we are interacting with OSHA as well on robotic safety.
Yeah, and we've had the alliance between OSHA, NIOSH, and A3, for about 6 years now. One thing that it has come out of that is the involvement in standards, but another is an update to the OSHA technical manual, which was published last year, I believe. So that updated chapter 4 of that manual, which includes information on safety with robotics, and really goes through some of those more federally mandated standards as well for safeguarding and things of that nature.
Thank you all. Thank you all for your feedback on it. I know our time's out for this, but I want to ask another question. Like, I think this is much more for Dr. Roedel and Dr. Carr. Like how can we adequately prepare for the future presence of robot in construction or similar fields and ensure their safe integration? What are your thoughts on that?
I can go first on this. So I'm taking definitely a more experimental first approach. Ideally, I think we would have laboratories or field conditions set up in much safer environments to test some of these interactions. And those are just facilities we don't really have readily access to. And so the field tends to be our laboratory. So I'd like to see that change. And obviously, you have to come into a mindset with some of these startups and some of these companies that are developing these tools with a safety first approach, and teaching that culture and starting there is always important when you're interacting with these companies.
And I guess the only thing I'd add there is, really a focus on risk assessment and risk management. I think is key to understanding what the state of the tasks are that are being conducted now that we potentially would want to automate or augment with robotics, to understand really what the risks are in the workplace, how robots can potentially be used to mitigate those risks, but then also what unintended consequences could happen by introducing these new technologies that may, inadvertently introduce new risks or exacerbate risks that have been there. So, taking that sort of approach, I think, is key.
Thank you all. Thank you all for your great presentation and for such a great roundtable discussion. I appreciate everyone in the session number 1, industry and government perspective, all the panelist member. I think we are 3 minutes late to start session number 2, which is focusing on academia's perspective. I want to Idris to take over from here and lead the webinar. You're muted.
There you go. Sorry about that. Thanks, Masoud, and thank you all for very informative presentations and very insightful discussions. I wish we had more time for the roundtable. But let's just switch gears now, and we heard about the government and industry perspective. Let's discuss the topic from a different lens. And in this session, we'll hear the academic or academia's perspectives on the research on human-robot interactions in constructions. So without any delay, let's start with our keynote presentation from Dr. Alexandra Medina-Borja. And Dr. Borja is a program director for Directorate of Engineering at NSF, and she's going to talk about human-robot interaction research and NSF's funding landscape in the construction context. Dr. Borja joined NSF in 2012 as a program officer in the Directorate of Engineering and has held several leadership positions since. Dr. Borja is one of the founding officers who spearheaded the Future of Work at Human Technology Frontier Core Research Program. And in 2013, Dr. Borja became the program officer for Human-Centered Engineered System Initiative in the division of CMMI. And currently she works with the M3X program, the cross-cutting cyber physical systems program. Dr. Borja holds an ME and a PhD in Industrial and Systems Engineering from Virginia Tech and a BS in Production and Materials Engineering from Federal University of Sao Carlos in Sao Paulo, Brazil. So thank you, Dr. Borja, for joining us. So I'll just let you take it up from here.
Hey, thank you so much, and good afternoon or good morning, depending where you are. And thank you for having me here. Let me just share my slides and make sure this works. Okay, can you see them well? Let me just reduce this so that I don't see myself. Okay, I think I have it here. So I was asked to talk briefly about the NSF funding landscape for human-robot interaction research. And I want to start by providing a little bit of an international context to this. Okay, and that is if I am able to advance my slides. Hold on. Yes, here. Okay. So from 2014 to 2023, agencies worldwide have invested around 925 million in research funding for robotics in construction in general. That is not focused only on the human-robot safety interaction, of which the European Commission, as you can see here, has provided the highest funding levels. But then NSF is I would say second, and third it would be the Japan Agency for Medical Research and Development. Now, okay, I didn't advance this, I guess. Okay, here. Now, if we focus on funding specifically for human-robot safety in the construction context, and we focus only in the United States and only funding provided by NSF, we can see that we have funded around 84 million in research for this specific topic, or around 9% of the total global funding for research. And 3 directorates are the main contributors to this: computer science and engineering, or SAIS, the Directorate for Engineering, and the new directorate, TIP, and I never remember what TIP means, but it's the directorate that now houses programs that were before at the IIT division of engineering. So things like the SBIR and PFI are housed now in TIP. Many of these awards, especially those after 2016, were funded by the now sunset Future Award Program, but certainly not all. So I am also here to talk about other potential funding opportunities that are now at NSF. So today I want to provide a summary of research topics that we have already funded under this umbrella, and the research that we are still interested in supporting more in the future. And just because I see that you have several international attendees, let me tell you that NSF, the agency that I represent, funds discoveries that enable the future. So we are interested, with the exception of TIP, that enables discoveries that are more applied. The rest of the foundation really funds discoveries that are fundamental in nature, so that the actual application will happen several years later. So let me just advance here. And then I will also talk to you about, some programs. So let's see. So today, first we are funding a lot of human-centered topics. And these are the ones that we see in the current awards. They are not the only ones. I just summarize those that are most common. The training and safety of construction workers in new robotic enhanced environments is one area certainly for which different technologies and training approaches have been used. Most commonly, we have funded a lot of virtual reality, augmented reality, or mixed reality that were used to provide realistic training scenarios to workers. And in the safety space, we have also funded many wearables, such as exoskeletons, as my prior speakers mentioned, but not only exoskeletons. In this space, there is also some algorithmic research or in trust building frameworks specifically, and how to incentivize trust in general as a safety precaution in this human-robot interaction that does not really exist yet, right? As you know, as we can imagine, there is still not this very intimate relationship between the human worker and the robot. And generally, what we see is still the human solo or only robots doing, and very, very little interaction between the human worker and the robot in a collaboration framework. Not necessarily as different projects. What I'm trying to say is that not necessarily the training projects do not have human-centered computing. Some of them have you know, several. So there is overlap here. Some have obviously a computing component, mostly machine learning or deep learning. And for the case of human-robot interaction, where prediction of worker intentions and movements is necessary, as well as understanding human dynamics, but also how we explain to the worker what the robot might do. So we have a lot of these algorithmic approaches. There is also a lot of activity recognition algorithms and post-estimation projects that we have funded. Most, if not all, also have a human-in-the-loop control system. Many reinforcement learning algorithms and optimization of motion trajectory in messy, unstructured environments, such as, you know, obviously a construction site, and similar things. So these are the things that we see usually that we have funded already, not necessarily that all the problems have been solved, but this is what we already have funded. So now I want to talk to you about the still unsolved important problems that we would like to see more proposals about. This is where solutions still need to be more efficient or safe for the human interaction with the robot. The first one, of course, is the co-adaptation, particularly in construction, changing and uncertain environments, dynamic environments. So we are looking for bidirectional and secure interaction that requires that the robot adapts to the physical environment and to the human worker or workers, understanding their kinematics, their behavior, and decision-making process. A prominent theme here is how the robot learns and how humans and robots co-adapt. We do not have, in this sense, mathematical frameworks to represent what we already know about humans in the physiological, cognitive, and behavioral space. So in the same way that we have physics-based machine learning, for example, we would like to see more proposals on human factors inform machine learning, human factors inform AI, and human factors inform algorithms in general. This problem requires, of course, that different communities get together and start thinking about this. We generally have, in the future world, we had a lot of interdisciplinary teams, but in the programs that remain, usually we have a bunch of engineers or sometimes human factors engineers as well, but very few computer scientists interacting with these other communities, and that is necessary. We want to advance this. I'm not saying that this is easy. This is really hard, but this is something that we believe is necessary for the robot to actually really recognize what the human wants to do, and the human recognize what the robot wants to do, and so that they can actually work together. Second, I would say the collaboration models for humans and robots in the construction site require research on task allocation and communication methods for these two agents to interact safely. And this brings us to finding the best way to display this information to humans. That's also needed. And we have funded a lot of research on that. That doesn't mean that this is a solved problem. So given construction workers' characteristics, unique characteristics, so we need to investigate usability, cognitive load, and all those things, and how you're going to display the information. As someone else said earlier, probably to a worker that does not speak fluently English. So now, so this is I forgot the last one is a very important one. Is multi-robot, multi-worker teams is still a very open research problem. So, having, different types of robots working with a team of workers in different tasks, that is a really messy environment, and that has still, this is even though we believe that's the future, we are still not there by any means. So very briefly now, I just want to go over NSF programs where this research could find a home. And first, the obvious one, and I want to address something that my prior presenter said, is the program that replaced the National Robotics Initiative, which is the foundational research in robotics. They have a bunch of program officers. The three ones that are my colleagues in CMMI are Jordan Berg, Alex Leonesa, and Siddiq Kidwai. And you can also write to the whole team at robotics@nsf.gov. And the big question here, okay, let me advance that slide. The big question here is if you want to think whether your research is suitable for FRR, is whether there is a fundamental research gap in the field of robotics. And if that is the case, and there is a goal of the project in which you want to give a robot or a class of robots new and useful capabilities that do not exist today, those are two important considerations. This could be in the context of construction, but the contribution has to be really to advancing fundamental research in the field of robotics. So that is FRR. And FRR, by the way, is open to other agencies, just as the NRI was open, to having MOUs with other agencies and collaborations with other agencies. So if other agencies here are interested in doing that, I recommend that you talk to Jordan Berg and make it happen. So what are the specifics for those of you who are academic researchers? So the good thing is that FRR does not have an explicit budget limit, or it doesn't have limits on the time frame for the project. Typical projects have an average of 150 per year, and typically 3 to 4 years, with the exception of career proposals that are always 5 years. And again, if you are interested in this, email the program officers, and this applies to all programs at NSF. Your best bet is to contact at least one program officer, send them a one-pager, and ask for feedback. The next program is, I am involved in this one, is the Mind Machine and Motor Nexus program, or M3X as we call it. And Alex Leonesa and David Mendoza work with me on that. Alex is the lead for this program. And basically, M3X supports fundamental research on the physical human-machine collaboration. It can be done in the context of construction safety. And it really, the difference with, for example, more algorithmic or software approaches is that there needs to be a motor function in the manipulation of machines in a sense, those machines could be a robot. And there needs to be some physical interaction in some way. The deadline, there is no deadline. This is a program that accepts proposals at any time. The average budget is $450 for 3 years. And again, email m3x@nsf.gov if you are interested. There is a program description on the web that has more details on what to look for and how you can know whether your project is suitable for M3X, which is really this bi-directional interaction with a human. And finally is the NSF Cyber Physical Systems. There are, again, this is a cross-cutting program with a lot of program officers. These are the three that are in the CMMI division, Ziqian Shen, Bruce Kremer, and myself. And the key here to know whether your proposal really suits the CPS, the Cyber Physical System, is that your contribution is on the Cyber Physical Systems gaps. So what is the cyber physical system? Is a system that has pervasive computation, sensing, and control. It's network in some way, and is dynamically reconfiguring and has high degrees of automation. And it can be applied. CPS is really agnostic about the application. So an application could be a construction site for sure. And CPS has project classes. They have more money than other programs that I just mentioned. So they have the small for them is an award of less than $500K, and frequently more focused research, and the medium is up to 1.2 million, and they do have something that they call a frontier, which is critical CPS challenges. And those are up to $7 million. And then they also have supplements for transition to practice that are probably very relevant to construction, in the sense that you can have these pilots of your research or your lab research on an actual site and see what happens, and they will give you funding for that. Of course, you have to have a CPS project first before you apply for the transition to practice supplement. Other potential funding programs that I'm not gonna go into details so that I can answer some questions is the human-centered computing. Of course, the big difference with M3X is that they do not require a physical system or a physical context. It can be, everything can be just computing. And then the civil infrastructure systems that, depending, I recommend that you talk to the program officer, Ziqian Shen, as well, whether this is something that she would be interested in funding. But it has to do with the civil infrastructure more than with a particular construction site. My best advice, always email the PO first. Do not call us. Very few of us actually answer the phone. If not, we will be on the phone all day. With that, I think I can answer any questions.
Thank you, Dr. Borja. That was a really interesting presentation and very informative. As Masoud also mentioned, so we did receive a lot of questions. Some of those we can discuss in the roundtable, but there's one that I really wanted to ask because you touched on it a little bit. So since the closure of NRI or Future of Work and similar programs that have been long supportive of construction robotic research, it's been a bit of a struggle to find the right avenues for projects that focus on human-robot interaction. While the programs like FRR you mentioned focus on core robotic research, or the contribution needs to be on the robotic side of it, do you think there is any specific program out there currently, or maybe some future plans that are tailored to support the research on the interaction or the safe interaction between humans and robots? Because this would be very helpful for the researchers in construction domain.
Yes, so the M3X is the obvious avenue, right, in that sense. That's number one. Number two is we have been working really hard to try to come with the other venues, especially to direct those future of work researchers, and some of them had just planning grants. And so to some other, depending on what the context, the work context is. And so stay tuned. We are still working on that, but one concrete venue is actually M3X. And the other one would be FRR with a, they actually, even if it is a human robotic interaction, as long as you have a robot involved, I think, they would consider your proposal. So in fact, just in preparation for this, I just reviewed their portfolio, and some of you have FRR funding. So that's certainly one of the venues there.
Thank you. Thanks for the great presentation. I really appreciate your time. So moving on, we are now going to have Dr. Burcin Becerik-Gerber from USC. Dr. Gerber is a professor and chair of Department of Civil and Environmental Engineering at USC and the founder director of USC Center for Intelligent Environments. She has pioneered an interesting new field of research, human building interaction. That's quite interesting. In 2021, she was elected to the National Academy of Construction and also serves on the board of Infrastructure and the Constructed Environment of National Academics of Science, Engineering, and Medicine. She has received numerous awards and recognitions, but the one that I love to mention is that she has received an Emmy Award as a co-producer of a documentary, Lives Not Grades, which told the story of a novel course that she co-designed and co-taught that focused on the engineering innovation for global challenges. So we welcome Dr. Gerber, and I'm going to hand it over to you.
Thank you so much for that wonderful introduction. I appreciate it. Let me share my presentation really quickly, and we'll take it from there. Okay. Just give me a second. Share screen. I will. Oops. Hold on. Wrong slide. Can you see my screen now?
Yep.
Right. So I believe I have about 10 minutes. Okay, I'll go through this really quickly. I apologize I couldn't be in the first part of the webinar, but I was able to catch Alexandra's presentation, and NSF has been a great supporter of this community. So I always thank in my presentations, but now in the presence of Alexandra in person, for supporting this community. So I will talk about the construction portion of my work in the lab. And I would like to start a little bit with what Idris mentioned, this human building interaction, so that everybody understands where I'm coming from to here. So I belong to this group called Computing and Civil Engineering, and we are very much focused on technology-enabled solutions. But I do like starting with this slide, and this is a similar conversation that I have with my students. Technology is the answer, but what is the question, right? Because of the technology, heavy involvement of technology in my research and our research, students come to us with an idea of implementing a technology. But I always try to have this conversation, couple steps back, what we are focusing, what is the question we're trying to answer. So for me, it is to use computing in support of individual and societal good. And this is at the center of everything I do in the lab. And if you narrow it down, it is, for me, human-centered built environments. These are the environments that focus on human needs, requirements, and societal goals. I'm actually changing this, even though I didn't change this in this slide, but I'm thinking about life-centered built environments, because I think our built environments impact more than humans, right? We have to think about life in general, and then our impact, hopefully positive impact in that realm. So Idris mentioned that I'm part of this human building interaction group. and with 3 pillars. We focus on, within the built environment, human performance and well-being through technological sensing and awareness that I mentioned, and during the building, design, construction, and operation. And there are several trusts that link these pillars, trust and collaboration, right, between machines and humans. And for me, building is a machine. Decision making and control in terms of human and societal objectives and the technology, and models and simulations that link the building side with the technology side. And at the center of this is the human and societal goals that I mentioned. 3 of them are here, but of course this list could be extended to safety, security, productivity, and other goals. So it does matter, human building interaction, because we spend so much of our time in the built environment. From construction sites to airports to offices to healthcare environments. And these environments, they're not only shelters or spaces for us to conduct work, but they could also be extension of ourselves, augment our human capabilities, and also support our goals. So that's where the idea of human building interaction is coming. Like, why, if we're spending so much time embedded within a built space, why can't we use that entity as also as a collaborator that support whatever action or task we're taking within that environment? So that brings me to this intelligent built environment idea that self-learn, predict, adapt, and change both their behavior, building behavior, and the user behavior. And there needs to be some kind of an interaction in a natural way between the users of the built environment and the built environment. And of course, they have to reason with a purpose. And this is where the user needs and requirements and goals come in place, like satisfaction, comfort, productivity, health, and well-being. So with that, I'm going to take you to the construction side, construction part of the presentation, because that's what we're focusing today. So as you can see, this is one slide I like using. There's semi-autonomous masonry robot, which was actually initiated through some funds from NSF. But why I put this slide here is, in every single picture that I could find when I was thinking about putting a slide about SAM, in short, that what it is called, that I found humans in the picture, right? Either they're working alongside this robot, they're feeding bricks, they're doing quality check, taking the excessive mortar. What does it mean? That means that in our domain, construction sites, we're very likely to have robots and humans working side by side. So we really need to think about the problem or the solutions from that perspective. And there's so many interesting questions. What is the relation between level of robot autonomy and trust to automation? And does the trust in automation change based on the type of or desirability of the task? Like, who leads the crew, right? If we're thinking about human-robot crews, like, is it the robot? Is it the human? And how do personal characteristics, I mean, that could be also on the robot side as well as on the human side, affect trust or collaboration? And most importantly also, how does robot-worker collaboration change construction work processes? Right, we're always trying to integrate technology within the well-known construction processes, but do we have to change those construction processes to adapt to the changing needs? So this is a picture that I took maybe 5 years ago on my way to work, and it says robots can't take your job if you're already retired, which I think it's an insurance ad, but I thought it was very interesting because as is yet another sign, we're signaling that robots are bad. Robots are going to take your jobs. But at the same time, I read this book. It's a very interesting book, in my opinion, a couple of years ago. That it says that it maps out there are human-only activities, there are machine-only activities, but there are going to be this human-machine hybrid activities where humans complement machines, where machines are not so good at, and then AI gives humans superpowers. And this is exactly where construction sits, right? It's in the middle. So with that, okay, yes, can human and robot agents work together to achieve shared goals? Yes, but upskilling and reskilling will be needed, right? And this is not actually, I'm realizing in the last 6 months with generative AI becoming really accessible to all of us, from engineering to marketing and communications to film, you name it, right? This upskilling and reskilling will be needed for actually every trade. So this was a cyber learning grant funded by NSF, where we worked on a novel VR-based training system with 7 different modules, where we try to understand if VR-based training impact on knowledge acquisition and knowledge transfer, and also safety, behavior, and skill set gaining, and trust in automation, situational awareness, and mental workload. So this is an interesting training where we integrated adult learning theories, and we have trained half of the workers during pandemic actually with VR-based training, and the other half of the workers in traditional in-person training with a professional trainer. Then we asked them to perform a demolition task with the real robot. Here you're seeing the same person operating a real robot. So it was, so some of these are some of the modules. In the first module, in all of the modules, we targeted operational skills as well as the safety behavior. From introduction of the robot to the range of motion, to how operators should position, what is some of the safety measures in terms of cable and operating zone and risk zones and boundary conditions, to how to use the controller, how to position the robot was in the 5th module, and how to position the robot safely, the arms length and the extensions and the angles between the cylinders and such, how to move the robot and safety concerns during the movement, and finally how to demolish the concrete slabs, floors, walls, beams, columns effectively, as well as safely, like how to position the hammer to prevent harmful bounces and such. So sorry, my Zoom is blocking and moving around. So it was interesting. In the interest of time, I'm going to not get into the details, but we did find VR-based training increased the knowledge of the robot, and participants had significantly better ratings from the expert trainer actually, and they had increased confidence in working with the robot and acceptance of technology. And they had more situational awareness. We did not find any significant differences in terms of mental workload, but some of these findings are attributed to the fact that with VR, the training is more accessible in the sense that you can have various tasks and various difficulty of tasks without concerns about setting up the training, without concerns about damaging the equipment or harming a construction worker. So in the VR-based training, workers were able to push the limits of the robot and see what happens in a safe environment. So that's, I'm not saying this kind of training is going to be in lieu of in-person training, but there are so many advantages to start and supplement with a VR-based training. But all of this research, it was very interesting for us. But as you know, one research door opens another research door. And while we were investigating VR-based training, we got into teleoperation. And as you know, many of the construction equipment are teleoperated, meaning there's some kind of a distant operation, but there is also remote operation. As you can see on the left side image, it is so the construction equipment is remotely operated, and you see all kinds of screens in front of an operator who becomes now an office worker in a way. So we started looking at teleoperation through the other work when we were doing VR-based training, and realized that there's so sensory information missing in current teleoperation equipment. So we started asking how we can provide vision, haptics, sound, speech, touch, and smell, and what are some of the important sensory information we need to bring to the remote operator who might be miles and miles away from the construction site. So this is an interesting approach we're taking here. We are adapting in this research stakeholder engaged approach and to design and test a sensory enhanced teleoperation workstation for demolition. And this group, C.S.P, we called, has 6 members, and we're working alongside them, and they're operators, trainers, supervisors, or managers in demolition companies in 5 different geographic regions with all kinds of experience and different perspectives. And they are, through interviews and focus groups, throughout research, informing what we should be developing and what we should be paying attention to in terms of the development. So we are providing various options to this group. So first, for example, during our first focus group, we aimed at understanding the operator's sensory needs. During traditional demolition, we organized the questions around different sensory modalities, started with vision, sound, and haptics. And with each sensory modality, we provided them different VR-based scenarios of like how they could be seeing or sensing these environments, as you can see. And at the same time, we also developed some very basic prototypes to understand the depth perception importance. If they want 3D sound or monophonic sound, or what should be the use of sonification, what kind of vibrating options they want, if they want single or multiple screens, and so on. So we had various findings in this. First of all, the multiple views is important. Depth information came really strongly, right? Because operating these machinery in 2D is not easy. Tilt information is extremely important for safety. They wanted to even know the smells, right? Because they're understanding with the smells, the status of the robot or the environment. Sound and haptic have dual nature. They inform the operator about the conditions of the robot, the task, the environment, but they can also be a source of disturbance. They prefer simpler designs, and personal preferences really played a role. And this is something dear to me because all my work is around personalization of environments. But at the end, they also suggested flexibility and control over the interface and level of feedback. They also recognize many important challenges. So decreased spatial awareness and its association with safety risks. So we have to be really careful there. The need for coordination with other crew members, right? There is the rebar cutting happening, and there needs to be debris removal. So teleoperation of one equipment doesn't mean that everything else is also robotized. Dust, a very practical challenge, right? And the cameras. And they also pointed out to age gap. I think I'm running out of time, but what we are doing with all of this is taking them into experimental conditions. And this is one experimental condition where we looked at sound, right? This is unfiltered and filtered sound. I'm not, oops, okay, excuse me. I won't be able to get into the details of this work that we're working, but we looked at filtered sound and unfiltered sound and looking at the number of collisions, reaction times, physiological responses, level of stress. But the idea, I think methodology is the most important part that I'm trying to give you the message here. It's the stakeholder engaged approach, identification important considerations, taking them to experimental setting. But then at the same time, we're working, of course, the physical setup. So we have a trailer, which we would take to different construction sites. This robot fits into the trailer, and we are equipping the trailer with also this teleoperation workstation that we're designing in parallel. So again, this is my last slide. I'm sorry, I'm taking longer than my allocated time, but we will be designing and testing some of the important considerations the group S.A.P. provided us, collision avoidance, the tracking system, and now we will be simulating these workstation operation, and we will be going to World of Concrete in January, where a lot of operators attend. And we will be testing with them and getting feedback. So it's not just SAP. And then at the same time, we're working on the physical teleoperation, the trailer, and we would be comparing the sensory enriched interface with the standard interface, not in VR, in real demolition scenarios. And once that is all done and throughout as well, we want to identify the interface to diverse underrepresented populations, because the main goal of this idea is providing these teleoperated operation stations, workstations, for opening the doors to female workers, opening the doors for disabled workers, elderly workers, right? You're not anymore like demolishing with your physical strength. You're demolishing on a computer in front of a computer workstation. So with that, I am going to thank, my students whose work I shared, my collaborators. It's an interdisciplinary team. We have a social scientist, health scientist, and in the previous one, we had a learning scientist, and of course, NSF for providing the funding for this important research. I'm going to stop sharing now.
Thank you, Burcin. That was really very informative. I wish we had more time to learn the details of the research. But I encourage all the attendees to read Dr. Gerber's papers, publications on this. They are really interesting. We did have some questions, especially about the use of VR, but hopefully we might get some time in our roundtable discussion to have more questions. So in the interest of time, I'll just move to the next presentation. And we have Dr. Boyi, and he is an assistant professor here at University of Florida in the industrial engineering, in the industrial and systems engineering. His research focuses on ergonomics, biomechanics, safety engineering, and human-robot interaction, particularly in identifying intervention pathways that influence and improve health and safety using emerging robotic technologies. He has been a PI on several competitive grants, including NSF, NIST, and National Institute of Food and Agriculture, and DOT. So over to you, Boyi.
Okay. So let me share my screen. I'll try to make it quick. Okay. So good afternoon, everyone. Let's go and get started. So the topic of my talk today is safety and biomechanics in occupational human-robot collaboration. So and since the theme of today's webinar is on construction safety and my construction HRI research, so the two organizers of the webinar will discuss and describe our collaborative work next. So the study that I will introduce is on other side of my research. So maybe this is out scope of directly related to today's construction safety, but I believe most of the technologies or the problems we introducing are universal. So objective manipulation and fine motor control related HRI can be applied in both agriculture, construction, and as well as other industries. So let's go and get started. I'll just try to get it quick. So my HRI research in agriculture has been focused on one very specific operation, which is the pollination. So the problem is it's very important because pretty much every 1 in 3 bites of our food needs pollinators, and the specific 87 out of 115 global food crops rely on pollinators. And on the other hand, the natural pollinators are in decline due to different reasons, and we have seen related articles and reports throughout the years. And next is this may be related to the previous guest speaker. So in terms of the agriculture building environment, we do not only have traditional open field agriculture products. So throughout the year, we are developing new environments for precision agriculture and other agriculture products, such as the vertical farming. And in the foreseeable future, we may even establish agriculture products in the space. While for most of these new building environment for agriculture, so there are not ideal workplaces for natural pollinators. And at the same time, agriculture, historically speaking, is not ideal workplace for humans either. So the data and the injury rate, so we can confirm this trend. So in many cases, agriculture is even more risky than construction and other industries. So to deal with this problem, so I participated in a series of projects, and we developed design and customized agriculture mobile platform to deal with the problem. Okay, so this is from the very early design and conceptual phase to the 3D AutoCAD and the fabrication and pilot testing and verification. And then this is the human in the loop experiment we did earlier this year. And we design and develop the platform from scratch, and the bottom line shows some of the actuators and the mechanisms we design and fabricate. And the final one is shows some simulation strategy that we designed to optimize the coordination between different robotic arms and humans. Okay, so this is the big picture. And so lesson learned through the research and HRI related challenges we identified. First of all, the navigation is not an easy problem. Agriculture, similar to construction environments, are very dynamic, less structured, and which requires very complex surrounding situation awareness and SLAM capability, and especially in the collective working mode, we'll have humans in the close quarter. So we need to design human-centered robot path planning and collision avoidance algorithm, which is not a trivial task. And next, in terms of fine motor control and object manipulation requirements, this is not an easy task either. So we utilize computer vision algorithm and plus other technologies, so to finish this task, to realize this function. And this video shows how we can identify a flower image, do the segmentation, and finish the path planning and finish the pollination operations. Okay, so that is the achievement from the previous project and ongoing effort. But in terms of the challenges, we identify the first one is in the real world, flower distributions represent significant perception and manipulation challenges. Flowers, they appear in clusters and they are facing different directions. And sometimes they are occluded by other flowers or branches, leaves, so which represent, not trivial perception challenges. And also the robotic pollinator needs to handle variations of flowers and plants variations. So the algorithm need to be adaptive to different environment. And also the effectiveness, including the success rate and the quality of the operation needs a significant improvement, which means we still need to keep human in the loop. Okay, so next is, as I'm trained ergonomics and biomechanics, so the focus or my primary interest is within the biomechanics and human safety side. So in this project, we just finished an experiment. We try to assess how pollination robots, collaborative robots, influence on the human biomechanical and the cognitive side of the during the operations. And in the experiment, we ask participants to simulate pollination operations by coloring QR code cards, and there were total 20 simulated flowers in each trial, and they were evenly split across 4 different height condition, which represent a different plant variation and flower distribution. And flowers were numbered, and the participants and the robots were assigned specific flowers to pollinate. And we included 4 different conditions in the study. So the condition number 1 was manual, which means the participants need to manually pollinate all flowers. And the second condition was without cue, which means participant pollinate 5 while the robot pollinate the rest. During the collaborative operation, no information about the cobas target was provided to the surrounding human participants. The third condition was a with cue condition, and the same number of flowers were distributed as the previous conditions. But before the task started, this time participants were notified of the cobas target. Okay, so we provide extra visual cues. And the fourth condition was the unreliable condition. And during this condition, the participants still knew about the robot's target, but this time the robot was not 100% reliable, means due to errors in terms such as computer vision algorithm and actuation, path planning, and the robot missed a certain percentage of the flowers, and the participants had to observe the robot and rectify the misses. Okay, so this condition represents a more realistic one. And in the study, we included 3 categories of dependent variables, including spine, biomechanics, actually the full body kinematics, and we also included the pupillary activation, which are used to investigate the human cognitive responses to this environmental stimuli. And we also include some of the subjective questionnaire and surveys. And here comes the result. I will quickly go over these. So the first significant result is unsurprisingly low plant height induce higher reflection angles. Okay, basically higher flexion angles is a good sign. It's negative for human workers. And next is the HRC, HRI had a positive impact on the lower and the mid-back joint angles. However, for the neck joint, there was an increased flexion, which means the introduction of the collab robot, they generate different impact on different body parts. And here's the detail plus. Okay, the benefit of HRC was more observable for the higher height condition, as you can see in these plots, with larger numbers reduction for HRC being observed. And for the neck angle, the negative effects of the HRC was more observable for the lower height condition. Okay, and next result is the unreliability negatively affects the gains made by HRC for the lower and the mid-back joints. And so this is a very important. So this conveys information that, HRC can be a positive thing, but we need to ensure that the system is truly reliable. Otherwise, all potential gains will be consumed by this unreliable condition. Okay, and here shows the fourth columns or the unreliable condition. You can see a clear trend reverse. Okay, and next, the introduction of the robot also decreased the rotation and the flexion angles for upper extremities. This is also a very positive sign, which means by introducing robot, we can successfully reduce the workload, the human side. And the final slide shows the robot most did reduce the perceived workload in most of the categories, but unreliability reversed the gains. And the robot modes are also reduced the anxiety about the cobas power and size, and this was not affected by unreliability. So, and the final slide shows the acknowledgement. This primary part of this research is funded by USD and NIFA, while the original review process was handled by NSF. This is the NRI-funded project, while the curriculum and outreach, workforce development aspect of this project has been funded by NIST and NIOSH. And the final slide shows the team. So this is a large team, interdisciplinary team. We have a robotics designer, control, computer vision scientist, and agriculture expert. And here's all my talk, and thanks for your time.
Thanks, Boyi. That was a very nice presentation. Appreciate your time. And again, we are already delayed, so we did have some questions to ask you, but hopefully I'm trying to club all of those together in the roundtables. So we'll move on to our final presentation, which would be by Masoud and me. We'll present our research, our contributions to this area as well. So I'll hand it over to Masoud first.
So somebody should read our bio, do you think? Or you can introduce yourself and then I can introduce myself. Okay, so I think you can see my slides. Hello, everyone. I'm Masoud Gheisari. I'm an associate professor in the Rinker School of Construction Management here at the University of Florida. I lead the Human-Centered Technology and Construction Research Lab at UF. I graduated around 10 years ago. Can't believe it, from Georgia Tech. And since then, I've had the incredible opportunity to collaborate with outstanding students and partners. Together, we have produced over 120 publications, secured over $2 million in external grants from NSF, NIOSH, Department of Labor. I also serve as an associate editor for ASC, Journal of Computing and Civil Engineering. Over the past decade, I have conducted research in the area of safe human-robot interaction in construction. And in this presentation, I'll provide a quick overview of some of our more recent studies conducted from 2020 till now. Let me see my clicks. We have extensively employed various small aerial and ground robots, including drones, wheeled and legged robots for safety-related application in construction. However, this presentation will mainly focus on aerial robots, commonly known as drones, and I delve into how we harness their capabilities for safety-related research in construction. Our research in this area can be classified in two specific categories. One, drone for safety, or how we enhance the safety on job site using drones. And the two, safety for drones, or how we can ensure the safe integration of these flying robots on the construction job site. So let's first start with discussing a few studies on the first area, which is using drones for safety purposes on the job site. One of our recent studies in this area was on how successfully such area robots can be used for safety planning and monitoring procedures. In this specific study, we used drones for the safety inspection of multiple high-rise building construction project. We investigated the practical benefits and challenges of drones for safety inspection on this job site using various data generated by drones, and studied how safety managers could integrate such technology and their generated data into their day-to-day safety planning and monitoring procedures, and finally proposed the process map for their successful integration. We also assess different types of drone-generated visual data, such as images, videos, and point cloud data, to see how useful they are for hazard identification purposes or other types of safety planning and monitoring activities. The main challenge in this study was that we were bombarding the one or two safety managers that not all the time they were on the job site with substantial volume of data, including like videos, images, and point cloud, expecting that, look, we have multiple drones flying around the job site, capturing a lot of data for you to do your job better. So in addition to everything you do on a daily basis to make the project safe, now just this is the dump of information. Go through this crazy amount of data to make informed decision quickly. So you could see how crazy our expectation was. So this brought us to another study after understanding how different type of data will benefit the safety manager. We focused on how we can better and quickly make decisions from this large amount of data that such flying robots are providing on the job site. In this specific case study, we focused on high-rise construction project where we employed drones to assist the limited number of safety managers on site. In this particular project, I think we had one safety manager who was not actually present all the time. So instead of safety manager walking multiple stories every day to check various safety features like guardrails, opening, and safety nets, drone provided them with an additional eye on the job site. We also developed a machine learning framework to aid them in reviewing the significant amount of visual data collected by drones for monitoring fall hazard, near unprotected edges, and openings. And these are some common issues in high-rise construction projects. And a three-step machine learning-based pipeline was developed to detect guardrails from visual data captured by the drones and provide a report for safety managers to point them to specific levels or locations that might have had guardrail issues. The outcome of this research illustrated that such automated AI-oriented system could improve the recognition of guardrails and facilitate the safety manager's task of identifying fall hazard in high-rise construction projects. In addition to focusing on the data collected by the drones, we also explored the hardware aspect of these devices to see how we could customize the aerial platform to meet the safety needs for flights on the construction job site. One thing we'll learn that the off-the-shelf platform might not necessarily satisfy the needs of certain groups in the construction domain, especially in this case, construction safety managers. So we ended up creating or building our own drone. The reality is that construction site with almost 1,000 fatalities per year are one of the most dangerous work environments. Like this is the number for only in the US. Now we are introducing robots, and in our case, the drones that would fly on top of workers' head. So this can lead to a more hazardous work environment. The idea was to consider changes that we can make to the hardware of the drone to make it fly safer on the side. In this specific study, we introduced and assessed iSafe UAS as the first drone platform designed for safety inspection purposes, featuring customized capabilities such as super optical zoom and a parachute recovery system. The results showed that just adding a parachute recovery system could reduce the fatality probability by more than 40%, which is very significant. I have seen other papers and research that are working on the airbag system on these flying robots, and more recent commercial drones from Skydio, for example, they included this. You can add the parachute recovery system to their drone. And this particular job site that we also customized the drone for, where we tested the iSafe UAS, it was flying we were flying more than 130 feet away from the building exterior. So although we were at a considerable distance, as you could see in these images and pictures, the super zoom capabilities aided us in identifying and inspecting many safety issues properly without the need to fly over the workers or get close to the building, or cranes that I think 2 cranes were present on the job site to expose workers and the people on the side more danger. Now that we wrapped up the drone for safety project, let's shift our focus to another series of projects that on safety for drones. And Idris, do you want to take over from here?
Sure, yeah.
So let me stop sharing, so that way you don't need to share the control. Okay.
Okay. Thanks. So my name is Idris. I'm an assistant professor here at Rinker School at University of Florida. And my research focuses on construction safety in general, but I'm more interested in this integration of technology and safety management, whether it's developing new technology to enhance safety of the work, or investigating the impact of new technology integration on the safety of workers. And I collaborate with Masoud a lot on many projects, especially on the latter part of it. So as we have seen today, and that drones are increasingly being used in construction, and while they have been very beneficial for various applications, including safety management, this rapid integration of drones into construction environments that are already very dangerous environments poses significant challenges to health and safety of workers, whether it's work safety, worker well-being, and whether it's the direct physical contacts or risks of physical contacts from drones, or it is the distraction caused to the workers, especially those who are already working in dangerous settings on ladders, on roofs, or it's the subtle emotional or psychological impacts of working with these, under these constantly buzzing drones. And then there's a big one, trust, especially with all the negative rhetoric about robots replacing humans. We need to make sure that workers trust these drones, have a positive attitude towards them, towards working with them or near them. It's not just only crucial for safety, but also critical for acceptance of drones. So as part of various projects, some funded by NSF and DOL, we have been investigating this complex arena of when drones and humans work together. And I'll present a few of our recent studies. So the first one investigates how drones impacts workers on heights. Why workers on heights? Because they are the most vulnerable population in construction. Most fatalities are reported in construction due to falling from heights. And coincidentally, drones also fly on heights, thereby having the most influence on workers on heights. So, of course, we couldn't do this experiment in real-world settings because of obvious safety reasons. So we relied on VR, like most of the HRI research. And we created these, we identified these 3 top high-risk scenarios from past accident reports that cause most accidents or fall-related accidents, and that would be influenced the most by drones, and then simulated those in the VR. So these were working on scaffolds, working on ladders, and working on roofs. And we place subjects in these immersive scenarios and ask them to perform very simple tasks in the presence of drones, while we use different variable sensors to record their physiological response, used eye tracking to record their attentional allocation, and also collected self-reported questionnaires. To obtain realistic responses, as you can see in the figure, we use some physical elements to provide haptic feedback. Say, for example, when they were on a ladder in a VR environment, they were placed on an actual ladder. So the results indicate that drones did not cause any significant emotional or psychological distress, but it did cause a distraction, which again could be fatal in these high-risk scenarios. Again, in full disclosure, this was done with predominantly younger population, so the results might differ with if we do a study with a slightly older population as well. And the next study evaluated the actual physical risks of drones, whether it's colliding with workers or colliding with equipment or temporary structures, scaffolds, ladders, and things like that. So we used 4D simulations so we can test as many parameters as possible, which is not possible with human experiments. So we created a dynamic simulation of construction scenarios with different types of drones performing tasks near workers, or tasks like delivering something, or and then the drones which do not need to interact closely with workers, such as monitoring or inspection type of tasks. And then we programmed different virtual workers in these scenarios, virtual equipments. They worked and moved about the site. And we varied several flight parameters as simulation parameters like speed, altitude, error rates of drones, and run these simulations multiple times, over 3,000 times per scenario, and to see if what is the likelihood of accidents, and how does this likelihood is impacted by these different flight parameters. So what we found was that the drones that operate at a distance from workers, like just tasks such as inspection or monitoring, have a higher likelihood of collisions with other equipment and ground. And drones that operate closer to workers, such as for delivery, have a higher likelihood of collisions with workers or buildings. Among the flight parameters, relative altitude influenced the likelihood of accidents for distant interaction drones, and failure rate, which was a kind of a proxy variable to account for human and technical errors, impacted the likelihood of collisions in most scenarios. This implies the need for improving the drone technology and better training of operators to prevent such errors. And also, this different influencing factors may also imply the need for targeted strategies for different work contexts. So we can't have a one-size-fits-all approach. And while we saw that the distance does impact the actual physical risk, we also wanted to evaluate if distance from drones also impact the psychological or physiological state of workers. So for this, we designed a very similar experiment. We categorized different drone distances based on Hall's proxemic zones and investigated if drones operating in these different spaces cause a differential or different impact on workers. And we again did a similar VR experiment with 4 conditions. And what we found was, while drone presence had some physiological impacts, particularly increased heart rate, the distance from drone did not significantly affect this impact. And another interesting finding was, contrary to what we expected, drones operating at some distance caused more distraction than the drones that operated in close proximity. So while this may seem counterintuitive, it is actually in line with other human-robot interaction studies, because although annoying at closer distances, the drone was maybe trusted more and accepted faster by the participants, as they could know and see the drone's intentions and clearly understand its future movement. On the other hand, drones or robots that operate at a distance may be assumed to have a more like a surveillance role, and which could provoke higher distraction. And at a distance, drones can also provoke more curiosity. So people tend to observe and have a clearer understanding of what drone is doing, where it's flying, what its flight intentions are. That causes more distractions. And finally, as we know that drones are here to stay, construction is the fastest adopter of drones. We are every year increasing our investments into drones. So we must prepare the workers to work safely with drones. So in one of the projects that we did with Department of Labor, we prepared a VR training environment where workers could explore the virtual site with different drones and learn about them. So the training included, information on the basic operation and use of drones in different settings, the current drones that we have in the construction sites today, and the future drones as well. And they learned about different application areas of drones, and at the same time also learned about different health and safety impacts or the risks from the drones in different conditions. So we simulated different accidents that could occur because of the drones or because of closely working with the drones. And then this virtual trainer kind of talked about those accidents. And finally, we also dealt with how we included some guidelines on how to work safely with these drones. So these were some of the projects about drones. We have some other projects that our team is working on as well. So the communication is a big one on that. So based on what we observed in earlier experiments and also based on research on safety, trust, and human-robot interaction, it's clear that having a clear way to communicate with drone can not only prevent physical risks, but it also helps workers trust more and have a more positive attitude towards drone. So we are investigating different interaction modalities to develop a communication protocol to help humans and drones communicate safely, and also conducting similar studies in VR and real world with other robots, which are also getting popular, such as these four-legged robots or wheeled robots. So all this could not have been completed if it was not for our amazing team of PhD students and graduate and undergraduate students who we work with and who have contributed a lot to this project. So I'll stop here. Thank you for being here. And I think we can move to the roundtable discussions. So let me stop sharing my screen. Okay. So like we mentioned earlier, we received a lot of questions to ask, but again, I wish we had the whole day or maybe more days to actually discuss these. These were some really interesting presentations from you all, and I'm sure attendees learned a lot, so did we. Among those many questions that we received, I think there are a few that we really wanted to discuss. So I'll start with you all. In your opinion, what do you foresee as the research direction in this field, in the field of human-robot interaction over the next decade, specifically in the workplace settings such as construction? So what are your thoughts? Where is the research going and or what direction is it taking?
I can start. I think that there is research on trust, that we have funded a lot of research on trust frameworks. That's number one. In the algorithmic sense, we also need to, as I said, fund more of human factors research in partnership with mathematics, basically, or computer scientists, so that instead of having just machine learning algorithms informing controls, we have actual human factors informing the machine learning algorithms that inform, that are using the controls. And that is a very hard problem. Coming with mathematic frameworks for humans or for human uncertainty, human dynamics, and everything is not an easy thing. But that until that happens, real collaboration cannot happen. So I think that those two, and then of course a lot of advances in robotics to make them safer. In the actual physical embodied robot, with the type of safety concerns that other presenters talk about. But I would say those are the three major things that we need to focus in the future.
Well, maybe I can jump in as well. In addition to what Alexandra said, I think there are, and I mentioned a little bit in my presentation, there are serious considerations for robotic-enabled construction processes. I think this is going to disrupt how we do construction work. I think we should go beyond inserting automation into our existing construction processes and start thinking what are some of the new construction processes that need to be implemented. So that is going to have a domino effect. It's not just within the domain of robotics or robotic operation, right? I mean, demolition has, I mean, I'm familiar with it. I'll give you an example. Demolition has debris removal, right? I mean, there are tasks that happen before and after and in parallel. So it's not just where you implement robotics, but like around it as well. So we really need to think about these construction processes, tasks, more holistically. And then the training is, I think, going to be important in this realm. I don't think we can forget about that because there's so much to do there. And at the same time, if we are truly thinking about human-robot collaboration, we really need to think about who leads the tasks, who are assisting, and how the handoff is done between a robot worker and a human worker. Specifically in complex tasks like construction where there's real danger to human life. So that I mean, those are some of the things that come to my mind.
Yeah, looking at it from a more holistic, as part of the system rather than isolated solutions to isolated problems.
I want to do a follow-up question on based on because Burcin, you added like training. So I think one of the most, if you want to prepare the future workers who are capable of working with such robots, we need to train them. Like we need to train our students and also the current workers to be able to work with that. But like, how can we prepare the next generation of the workers and professionals to interact with these robots when we don't have access to many of those robots, especially like institutions like universities or that we don't have access to such robots, how they can train the students and professionals to be prepared? So that's a question for everyone.
Well, I'll jump in very quickly. I mean, VR is one way, right? I mean, it's not going to take away the in-person training. Of course, this is always going to be important, I think. But I think more novel ways of training, not just like use VR, but more personalized, more experiential learning embedded within VR could be a way. When you were talking about asking the question, I also thought about like shared equipment. I think this is going to be important for educational institutions. Like maybe in Southern California, not all of us can have a 3D printer, life-scale 3D printer, but maybe we can think, I mean, this is my administrative hat, I think how we can create shared resources where we can take our students to nearby universities and they come to USC and such. So we have these hubs in a way. And collaboration with the industry is going to be important, right? If they're going to be implementing these on their construction sites, maybe there could be an opportunity there as well.
Thank you. I think just a couple of minutes, so that one last question to everybody again. So what roles do universities and funding agencies play in ensuring the safe integration of robots in human-populated workplaces? maybe in collaboration with others, we asked the similar question to NIOSH as well. How do they support the safer integration of robots in the human populated workplaces, and also the universities, which is something Burcin alluded to, by training the next generation of students?
Well, as you all know, we fund research, and as part of research, first in the research we have, you have all to have human subjects authorization and all those things as part of the research. Now, as programs for the real population, and there are programs at NSF like the cyber, I'm not gonna remember exactly the name, but a trust cyber infrastructures. Well, there is a program about safety in cyberspace that applies also to robotics, and that only funds research on that space. And I think there was a question here about, and this is one of the unsolved problems, right? So if you want to take physiological measures from a human and then put it in a robot, of course, there are a lot of confidentiality and privacy concerns. So those are unsolved problems that we have, but there are things that we need to start thinking about.
So I'm sure all of you are busy, and so I'm not going to take much of your time. So I think I'll just thank you all for joining us and having a really successful webinar. I think we all learned a lot during these presentations. And so the next steps, we are going to share the webinar recording very soon with all of you. And we are also going to prepare a white paper based on the discussions that we had today, and share that with you all as well. So thanks everybody for joining us.
Thank you, everyone. Thank you.
Thank you for the opportunity.
Thank you, Burcin.
Thank you so much. Bye-bye.
I'll end the meeting.